Okay, moving into chapter 7, which is called probability. Okay, what is probability? What are we going to be doing with it? Okay. Okay. Probability can be thought of as just a measure of how likely something is. 7.1 is called Introduction to Probability. So we're going to be discussing how to measure how likely something is here. And then 7.2 and 7.3 are going to be just more advanced, basically expanding our pool of examples to include things that are basically harder to count. So 7.2 is going to be counting, quote unquote, counting methods, combinations and permutations, which is going to be able to, the purpose is it expands the number of situations we can talk about for calculating probabilities. But first, just an introduction to probability and what it is. So we can think of probability, like I said, probability in the most basic sense is a measure of how likely something is to occur, is a measure of how likely, I'll just say an event is. For instance, you already know intuitively that the probability, or you already have an intuitive idea of how to measure how likely something is. For instance, if I said, how likely is it for you to be struck by lightning right now? You would say very unlikely. Okay, it's technically never impossible, right? I suppose that you could be struck by lightning at some point, but it's extremely unlikely, right? What is the probability? I should have gotten this ready before. Let's see. Let me get some coins here. What is the probability of flipping a coin and getting a heads? So I'm going to be using props for this lecture, by the way. So what is the probability? What is that? Okay, that's tails. It's like a bat. It's like one of those special, it's like a zoo quarter or something. I don't know. National park. Anyways, heads, tails. What's the probability of flipping this and getting tails? And you may intuitively know that it's 1 out of 2. It's 1 out of 2, right? But how do we know it's 1 out of 2? And by the way, that's 50%, right? So if I flip it again, I get another tails. But if I flip it enough, if I do it enough, those numbers of heads and tails should even out. So there I got 2 tails and then 2 heads. Okay. So we already know intuitively about the likelihood of some events, right? If it's a very extreme event, like extremely unlikely, like being struck by lightning, then we have an idea of the measure of how likely that it would be nearly 0, right? The probability would be nearly just not possible. We know that if something is extremely likely, like what's the likelihood that we will all die someday? It's, well, maybe that's a bad example. Well, anyway, that's fine. It's extremely likely, right? It's extremely likely, unless science just, there's a huge boom in science in our lifetime and they figure out how to make humans immortal, right? So these extreme events, we have a good idea about how to measure those probabilities. We can't apply numbers to them necessarily, but we can talk about them. And also for calculating the probability of something as simple as a heads or tails, so just 2 possible outcomes, we can talk about that, right? We can actually apply numbers there. If we just think about it a little bit, flipping a coin and getting heads or tails, it's 1 out of 2. Right, a 1 out of 2 chance, or a 50% chance of getting a heads, or a 50% chance of getting a tails. What about if I asked you the probability? How would we measure the probability of taking a deck of cards, and if I randomly pull a card, what's the probability that it would be a 4? A 4. So that might not be as easy, right? Because how do we measure that? Like, how many possible outcomes are there? What's the possibility? What's the literal measure, like as a number, of me drawing a random card and getting a number 4? Let's think about that. So first of all, though, just in case any of you aren't familiar with how a deck of cards works, there are 4 suits. There's diamonds, hearts, oh look at that, clubs and spades. Diamond, hearts, clubs, and spades. So 2 red ones, hearts and diamonds, and 2 black ones, clubs and spades. And then there's 2 through 10 as numbers. So there's 2 through 10. So you see here's a 9 of hearts and a 5 of hearts and an ace of clubs. There's 2 through 10, and then there's jacks, queens, and kings, and then ace. So let me see if I can find examples of those for the hearts, just to show you like what one whole suit looks like. I had these pre-shuffled. Maybe I should have put them in order first. So the 3, the 4. Maybe this isn't necessary. Maybe everyone already knows how cards work, but I've had classes in the past where there's at least one person who wasn't familiar with the structure of a deck of cards. Did I not have a king? Oh, there, never mind. Okay. I hope this is a full deck. All right, so we have all of the hearts here. We have 2, 3, 4, 5, 6, 7, 8, 9, 10. So how many cards is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Because we're not starting at 1, so this is 9. So 2 through 10, and then we have jack, queen, king, and ace. So there are 13 hearts. There are 13 hearts, 2 through ace. 13 hearts, and if there are 4 suits, right, 13 of each kind, then there are 52 cards, 13 times 4. Okay, so that's just a quick rundown of how a deck of cards is structured. Now that I have these, I need to reshuffle these. So as I'm reshuffling, I'll try to discuss what we are going to try to do, which is figure out how to measure different probabilities based around a deck of cards, because a deck of cards is a nice little real life example of they're just great examples of differing types of measures of probability. So back to that first question, I said, how likely is it for us to pull a random card that's from a well-shuffled deck, which I'm working on right now, and what's the likelihood that it'll be a 4? And literally, I want a number, like a percentage. What is the percentage, the probability that I'll pull a 4? So let me write that question down. So I want a measure of this. Now, how can I figure that out? Well, consider the coin flip experiment. We said that the probability of flipping a coin and the probability of getting a heads when you flip a coin, the probability is 50%, 1 out of 2. Where did that 1 out of 2 come from? Where did that 1 out of 2 come from? Well, the 2 came from the number of possibilities. The number of possibilities. So consider the coin flip. We said there is a 1 out of 2 or 50% chance to get a heads when flipping a coin. 1 out of 2, 50% chance to get a heads when flipping a coin. The 2 represents what? Represents the total possible outcomes when flipping a coin. Right, why is it 2? Well, because there's only 2 possibilities when flipping a coin, right? You get heads or tails, right? Heads or tails. So there's only 2 possible outcomes when flipping a coin. That went in the denominator, which seems very intuitive when you're just thinking about, you know, heads or tails. And you think, okay, it's 1 out of 2. So I'm kind of pulling apart this intuitive example, and we're going to apply these ideas to the to this question about pulling a 4 from a deck of cards. The 1 represents what does the 1 represent? What does the 1 represent? Let me see, am I using the wrong terms here? No, that's okay. The 1 represents the number of ways. Sorry, I was checking how the book uses the word outcomes, and it's okay. It's okay. I'll make it clear when I write down the actual definition of probability. The 1 represents the number of ways. The number of ways to get what? To get what we wanted, which is a heads. Because of course there's only one way to get a heads, right? When you flip a coin, there's just one way to get a heads. Okay, so we have this fraction that is the number of ways to get, I'm going to say, a 4 from a deck of cards. Divided by the number of ways. So I'm just lining it up with this description about the coin flips. The number of ways to get a number to get heads would be in the top, right? So now I'm just saying, well, the number of ways to get a 4 from a deck of cards instead of getting a heads when you flip a coin. Number of ways, or number of, sorry, let me say possibilities in a deck of cards. I'll just say from a deck of cards. So if I just force that thinking from the coin flip into this new example about pulling a 4 from a deck of cards, this is what I get, this fraction. All right, let's see what this gives us. So number of ways to get a 4 from a deck of cards, but how many 4s are there? There's not one, right? There's excuse me. There's the 4 of hearts, the 4 of diamonds, the 4 of clubs. How do you draw clubs? And the 4 of spades. So the 4 of clubs, which is like a boop, 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 boop. 4 of clubs, and the 4 of spades, which is like a okay, upside down kind of heart thing like that. Okay. There's 4 of them, right? Because there's 4 of each type of card. Like if I said, you know, how many 9s are there? Well, there's a 9 of hearts, 9 of diamonds, 9 of clubs, and 9 of spades. And in the case of a 4, there are 4. There's 4 of hearts, 4 of diamonds, 4 of clubs, 4 of spades. So there are 4. So the top of my fraction, the number of ways to get a 4 from a deck of cards is 4. It's just coincidence that the number is the same. It's right. It would be 4 for any numeric value of a card. How many possibilities are there for pulling a card from a deck of cards? Total possible number of cards, right? That's what I'm looking at, number of cards here. And remember, I said earlier, it's 52. For a coin flip, there's only 2 possibilities, heads or tails. But for a deck of cards, there's 52 possibilities. 52 possibilities because there are 52 total cards here. What is that as a percentage? Recall to do this as a percentage because that's what we're going to want. We're going to want our probability written as a percentage most of the time. You're just going to do 4 divided by 52 in the calculator. And then multiply by 100. And I'm getting 7.69%. I'll just round, yeah, 7.69%. 7.69%, so fairly low, fairly low. So if I was to, let me shuffle these a little bit more, and then I'll pick a random card, and there's a strong chance, like, what's the percentage of not getting? Here's a good question. What's the percentage of not getting a 4? Or the probability? What's the probability? Probability of not getting a 4. Well, it's just any other card, right? So I could take 100% minus the 7.69%, which would be 92.31%. In other words, what's the chances of getting a 4? It's pretty low. It's about roughly around 8%. What's the chance then of not getting a 4? Well, it's the opposite. It's 100% minus that. So really high chances of not getting a 4. So I've shuffled them. If I just randomly pick a card, like it's not a 4, right? How many, if I stuff this back in the deck, because I should have 52 each time, how many would I have to keep drawing? In order, so really I should be reshuffling each time. How many would I have to keep drawing before I get a 4? Well, I don't know, but it'd be, you know, a lot because it's a pretty low chance of me getting a 4. You know, I could, there's one finally, right? So the point is there's only 4 in this deck of 52. There's only 4 4s, so it's a low chance. This is how we measure probability, okay? It's a fraction. It's a fraction of number of ways for an event to happen divided by the total number of possibilities. Sorry, I'm pre-shuffling these for later experiments. Okay, so let's write this down. But first, let's write down some definitions. A trial I'm just going to say it like this, is a, probability experiment. Okay, like pulling a card or flipping a coin or rolling a dice or, you know, things outside of the, you know, like could come up with real world examples. Measuring being struck by lightning, you know, what would the trial be in that case? That's a good, you know, that's not a good example. Just any probability, a single probability experiment is called a trial. Outcome. The outcomes of a trial are the possible individual results. So, for instance, for the flipping a coin, this was just 1. The possible individual results, it's just, well, the size of the outcomes was just 1. For flipping a coin, if I want to get a heads, then the possible individual results is just going to be the heads, right? If I want to pull a 4, then my possible individual results, my set of outcomes are going to be the 4 of diamonds, 4 of hearts, 4 of spades, or 4 of clubs. Okay. Sample space of a trial. This is the set of all possible outcomes. So for the cards, The set of all possible outcomes is not 52. That's the size of the sample space. But the actual, if I said find the sample space for the experiment we just did with pulling a 4 from a deck of cards, to find the sample space, you would have to list all of these cards, all 52 of them. Or maybe you could find a shorthand way of doing it. You could just say, you know, sample space is any card from a standard deck of cards. But really, like if you were to list out all the possible outcomes, you would need to list all of these cards, all the possible outcomes. But what we're really concerned with is the size of these spaces. An event a subset. This is a subset remember that terminology from chapter 2. Remember I said all that set theory stuff, or set notation and set theory stuff was building up to talking about probabilities. That's why we looked at that. So here it's coming right out of the gate here in 7.1. A subset of outcomes in the sample space is called an event. So an event is a group. It's like a whole chunk of possible outcomes. Okay. Okay, so what we've been talking about is called classical probability. So-called a theoretical measure of how likely an object, or of how likely an event is to occur. I'll just say how likely an event is. So what I mean by that is when I say that there's a 7.69, I'll just say 8% chance of getting a 4, that doesn't mean that if I randomly pull a card, like that, what does it mean? You know, we have to be careful about what we're saying here. I could randomly pull a card right now and have it be a 4, right? Like I could just randomly pull a card and have it be a 4. Right now, I peeked to make sure that I pulled a 4, right? But so just because theoretically we're saying it's an 8% chance, you know, that doesn't really tell us a whole lot about what might actually happen in the real world. It gives us an idea, right? That's called a classical probability. It's like a theoretical measure. It's still good to know, right? That's what we're measuring here. So why am I pointing out, like giving it this new name, classical probability? Well, because we're going to compare it to another type of probability later in this section called empirical probability, which is more about conducting a bunch of experiments and getting a measure from there. But this classical probability is calculated like this: probability of some event. So some event like pulling a 4 from a deck of cards is equal to the number of possible outcomes in the event. Because remember, an event is a whole group. Gonna need a bigger fraction bar. Divided by the number of outcomes in the sample space. In the sample space. All right, so let me break this apart for you. So this is read as the probability. So I could say, like, tying it to the example we just did, probability of pulling a 4 from a deck of cards So this is the event. That's the event right there. Pulling a 4 from a deck of cards, that's in parentheses here, is equal to, big fraction, the number of possible ways to pull a 4. The number of ways to get a 4 over the total number of cards. That's how I interpret this definition as it applies to this example with a deck of cards. And of course we got that it was 4 over 52, because how many ways are there to get a 4? Well, there are 4 ways. Say roughly 8%. Okay. Some quick notes about this classical probability, about literally the numbers it can give you. The probability of an event should always be between 0 and 1. Like you can't have a negative probability and you can't have a probability greater than 1. In terms of percents, what I mean is in between 0% and 100%. You can't have anything more likely than being 100% positive to happen, right? 100%. And you can't have anything less likely than being 0%. Just doesn't make sense. So your probability should always be, when you write them in terms of a percent, between 0% and 100%. Okay. All right. Let's do some practice looking at determining sample spaces. So this is example 1 in the text. So recall that the sample space for my deck of cards is all 52 cards. The size of my sample space is 52. It's important that those are two different things. The sample space itself is all of the 52 cards, like literally listed out, and the size of the sample space is 52. Identify the sample space for each experiment. Then state its size, the size of the sample space. Okay, part A is rolling a six-sided die. Die is singular for dice. Wait. Yeah, that's right. If you have more than one, they're called dice, but if you have one, it's just called die. Okay. Oh, I actually have one. Back before quarantine, when I used to be a nerd and play D&D every once in a while. There we go. Okay. I don't need all those. So a six-sided die. There we go. 1, where's 2? 2, 3, 4, 5, and 6. Those are the possibilities. So if I list the sample space, I don't want it to just like list the numbers. I need to like, I'm going to denote them with a set, because a sample space is a set, right? So set brackets coming, recall that, set brackets. And I need to like notate this somehow. And I know it's just a number, but really what I need to do is make sure that I'm noting what's actually happening. So what I'm going to draw is, what I'm going to write is I'm literally going to like draw the dice. or the die rather, and write the number 1 inside. Then the next one, the next possibility is a 2. The next one, so why aren't I just writing the numbers? Also, these are supposed to be the same size. I just suck at drawing squares, I guess. Why aren't I just writing the numbers? Because the sample space is not a set of numbers necessarily, unless that's what you're measuring. The sample space is literally supposed to be the physical thing happening in the real world. So my sample space here is not the numbers 1 through 6. It's literally the different possible rolls that I can get. It's a side of a die. It's the side of a die, literally the side of a die, not just a number. Right. Now, what is the size of my sample space? So this is my sample space. What is the size of it? In other words, what's the cardinality of it? How many elements are in this set? The size, of course, is 6. Okay. What about flipping 2 coins? All right, flipping 2 coins. Oops, sorry. Let's see, do I have any normal coins? I just want like a regular. All the quarters I picked are all those like special ones that have states stuff on the back. Okay, we'll use Kentucky and Massachusetts. All right, flipping 2 coins. What is the sample space? What is the sample space? Well, consider this. Oops, hang on. I'm flipping 2 coins, right? Not just one. Here's my first possibility. 2 heads. Heads, heads. I'm going to notate that with H, H. So you kind of get to decide how you notate this, right? I could literally draw like circles and then George Washington's face, but I think that's a bit excessive. I can draw it with the die up here because it's literally like squares with numbers. But here I'm going to notate these with H's for heads. Okay, what other possibility can I have? I can have heads, tails. So this second quarter giving me tails. Or I could have tails, heads. Right, tails, heads. Or, whoop, tails, tails. Those are the possibilities. And these are distinct here. Those are the possibilities for flipping 2 coins. And the size is 4. Right. Why is this important? Why is it important to notate the sample space, say for like part B here? Well, consider this question. Now I can answer a question like, what is the probability of landing double heads when I flip 2 coins? Well, I know it's going to be a fraction. It's going to be a measure. I know the size of my sample space when I flip 2 coins is 4 from part B. How many different ways, how many different possibilities? Looking at the sample space, how many different ways are there to get a heads? I mean, to get 2 heads, Only 1. So that's 25%. Okay. I can also ask another question like, what is the probability of landing heads and tails in any order when flipping 2 coins? Well, look at my sample space. My sample space, so the size of sample space is 4. How many different ways to look at find the numerator? How many different ways can I land a heads or a tails, or heads and tails, but in any order? Well, 1, 2. 2, right? So 50%. So that's pretty likely. I could ask another question. Yeah. I could ask all sorts of questions, but here's another one. What is the probability of landing at least one heads when I flip 2 coins? Well, I know my sample space size is 4, so that's my denominator. What about the numerator? The probability, hang on, sorry. Oh, I got too much junk up here. These dice are getting in the way. All right, let me put those over there. Okay. There we go. What is the probability of landing at least one heads when I flip 2 coins? So I'm going to look at my sample space. These are all the different possibilities. How many of them have at least one heads when I flip 2 coins? How many of them give me at least one heads? Well, 1, 2, 3. The last one does not. So that's 75%. Good chance. So that means if I go ahead and flip these 2 coins, I should have a pretty good chance of getting at least one heads. So I'll flip 1. That's tails. Of course, I get double tails. It's double tails. Anyways, let me do it again. There's at least one heads, right? Heads and tails. If I do it again, if I do it 4 times, I should expect it to happen 3 out of 4 times, right? Okay, I already won this one. Okay, I got at least one heads. They're heads, tails, so this is fine. So that's 2 out of 3 so far. And look, heads, tails. Okay, so that was 3 out of 4 of them landing on at least one heads, which checks out with. That's funny though. That of course, the very first one I did, I get double tails. All right. So this is all calculating like theoretical probability. Theoretical probability. Okay. Let's do another example with a deck of cards. So here's what I'm going to say. Let our sample space be a standard deck of cards. Cards with 52 cards. Part A. So, you know, I said that if you actually wanted to list out the sample space for a deck of cards, you would literally have to write all 52 cards down, like King of Diamonds, 10 of Diamonds, Queen of Spades, 2 of Clubs, 5 of Spades, literally all 52. Much easier to just say it in words, like just let the sample space be a standard deck of cards with 52 cards, right? So the size is 52. What is the probability of drawing at random? So at random, of course, a red card. Well, I know that my sample space size is 52. How many red cards are there? Well, recall that there are 13 of each suit. There are 13 diamonds. Ooh, I don't want to, let's say 13 diamond cards. I'll just say it like this, 13 diamonds. There are 13 hearts. I don't have a black marker. I have a black pen. Probably won't be able to see this as well, but I just want to emphasize red versus black. So 13 clubs and 13 spades. Okay, so how many different ways are there to possibly get a red card? Well, I could, if I pull a diamond or a heart, it'll be red, so that's going to be 26. Oops, I meant to use the same orange there. 26. And what is that as a percentage? Well, just pop it into the calculator, 26 out of 52, and of course it's going to be 50%, right? Because half of the cards are red. Half of the cards are red, so what's the probability of me pulling a red card at random? Well, that's pretty good. It's a 50% chance. Let's see. I got one. Okay, I got one. 50% chance. What's the probability of pulling a black card at random? Well, of course, it would still be 50%. How about, what's the probability of pulling, this would be part B here, what is the probability of drawing, of course, at random again, a diamond? Well, my sample space is still 52 because I'm pulling from an entire deck. But how many diamonds are there? There are 13. What's that going to be? 13 divided by 52, and then times 100 to make it a percent, 25%. So a quarter chance. So let's see if I just, did I shuffle again? Whatever, I'll pull from the middle. Less, so I probably shouldn't get a diamond, right? Probably shouldn't if it's only a 25% chance. Let's see. Oh, I got one. Let's see. Let's just for, yeah, there's one that's not. So, you know, you can see how this is theoretical probability, right? Like it doesn't guarantee, you know, anything. It's just a measure of how likely it is to draw a diamond. So if I do it again, having shuffled, that's not a diamond, right? If I put that back, pull another one, that's not a diamond. So 3 out of the 4 cards I've pulled so far are not diamonds. If I don't know, pull another one at random, not a diamond. There's a diamond. Not a diamond. Getting a ton of hearts. Here's one. There's not a diamond, etc., etc. Okay. Here's a different question. Let's move to part C. Let's change the sample space a little bit. Suppose you are dealt. So whenever someone's dealing cards, I mean the cards you are dealt. Okay, so that's just the past tense of deal. So you are dealt 13 cards. So you got 4 players dealing out all the cards. Oh, wait a second. Wait a second. Let me think for a moment. I don't want to make this too complicated. Let's see. Nope, never mind. This is going to get, this isn't what I want to do. Let me change it. Part C, I'll just stick with what the book is doing. What is the probability of being dealt a quote-unquote face card? Like one of those royalty cards. That's king, queen, or jack. Okay. So, or drawing at random. So I'm ignore this. Right, so we're still drawing a card at random, so my sample space is still 52, or either being drawn a card at random or you're being given a card at random, whatever, doesn't matter. What's the probability of it being a face card? Well, how many kings are there? There are 4, right? Diamond, club, heart, spade. How many queens are there? There are another 4. How many jacks are there? Another 4. So that's 12. And what is that as a percentage? That's going to be roughly 23%. So if I randomly deal a card, it's a pretty low chance. if I randomly pick a card or deal you a card, pretty low chance that it'll be one of those royalty cards. So let's just pick one at random. Yeah, it's not. Okay. All right. Okay. Example 2, 3. Example 3. Suppose that you grab a snack from a bag of chocolates that contains 4 caramel with milk chocolate, 4 peppermint with white chocolate, 6 dark chocolate with mint, and 2 raspberry with dark chocolate. What is the probability that you randomly grab a raspberry with dark chocolate? Okay. This is example 3 from the text. I'm going to kind of abbreviate this. 4 caramel, 4 peppermint, 4 mint, which is different from peppermint, right? And 4 raspberry. No, how many? 2 raspberry. 2 raspberry. Oops. That contains 4 caramel, 4 peppermint, 4 mint, and 2 raspberry. What is the probability that you draw, or not draw, that you pick a raspberry? Well, I need to find my sample space. Sample space is the total number of possibilities. 4 plus 4. Oh man, what? I got all mixed up. This is supposed to be a 6, right? Yes, this is 6. Trying to follow along with the example, that's 6. Just misread it. Okay, so 4 plus 4 plus 6 plus 2 is going to be my total. So what is that? 16. 16. That's my sample space size. My sample space is all the chocolates. The size of the sample space is 16. Now, how many different ways are there for me to pick a raspberry chocolate thing? Well, 2, because there's only 2. That's going to give me 1/8. I don't really need to simplify the fraction, I suppose, unless if I'm asked to give the probability as a fraction, then this would be my answer. If I'm asked to give it as a percentage, then I would change it to percentage form and get 12.5%. Okay. So in the next part of this lecture, we're going to talk about empirical probability, which is more of it's a measure of how likely something is to occur based off of a great number of experiments, instead of just looking at sample space versus event space size. So that'll be part 2 of this section.